But let me start my talk here. Non-equilibrium thermodynamics of open quantum systems. And yeah, Santoda invited me to talk about this work. So here are some of my academic movements from SN Bose Center to various places, and some of my recent collaborators here. And so uh, the title is Non-Equilibrium Thermodynamics of Open Quantum Systems, but I will start from the last part, that is open quantum systems. So I will talk about a little bit about open quantum systems and the motivation. Why do we study that? So basically, open quantum systems are basically many-body quantum systems where you have a quantum system which interact to their environment. So and the motivation is because in reality, or the realistic quantum devices, they usually interact to their environment, and essentially they are many-body quantum systems, as I said. And we are interested in how does this interaction influence the open quantum system, causing dissipation and decoherence. And we are interested in the equation of motion or the dynamics of some physical observables uh, of the open quantum systems under the interaction of the environment. Usually what happens when a system interacts with the environment, we have dissipation, decoherence. We start with a pure quantum state, and it gets decohered uh, and becomes a mixed state. So we need to handle mixed state for that, so that yeah, here again the motivation, these controlling decoherence is, I think, is the most important thing for the experimentalist, yeah, for quantum systems. And here are some examples of open quantum systems I'm showing here on my screen. Like a two-level atom interacts with a cavity photon. We studied from our batch masters, actually, and these are textbook problems. But nowadays, this kind of atom photon interactions are realized with artificial atoms, like using, for example, superconducting qubit and some resonators interacting with it. So all of these systems are, or better to say, devices are actually open quantum systems. They interact with the environment, and we need to know how that interaction actually affects. Yeah, sorry. Hello. Is there any question or?
Carry on, Moni.
Okay.
Carry on.
Okay. So there are other examples like qubit realization using quantum dot. For example, here I have shown with double quantum dot here. So these are the examples. Other examples are, for example, various kind of cavity, like using photonic crystal cavity, and LC circuit using superconducting Josephson junction device, and various hybrid optomechanical systems here in the left side. I should use the mouse here. Yeah. So these are also examples of open quantum systems. And here there are more here. I mean, hybrid quantum systems, as I have mentioned. So how, I mean, using these hybrid quantum systems, actually you can transmit or process quantum information and transfer a quantum state from one type of system to another type of systems. So these are different physical systems, but they can be coupled or engineered. All of these are also examples of open quantum systems. And lastly, I think I should mention this also, like nanoelectronic devices where you have uh, another name is people used to say quantum transport. Uh, electron transport through these quantum devices, and we have some coherence properties for these nano electronic systems, and they also interact with their electronic reservoirs and they can be treated as open quantum systems. And from another perspective, I will come to that later. Okay. And of course, quantum computation is another motivation. And when you deal with a noisy environment, then you need to handle open quantum systems. Uh, and in various quantum information protocols also, how does this protocol work, or their fidelities behave under noisy channels. So yeah, and this is the last one. I think this motivation for open quantum system is that quantum measurement process, and we have I mean we know about these quantum measurement problems, like when how does different outcome of a measurement appears if we start from if you only stuck to Schrodinger dynamics, that is unitary evolution. Then Zurek actually came with a rescue using his decoherence model, where he actually treated the apparatus as an open quantum systems which interacts with their environment, and then he explained the measurement process, quantum measurement process. So overall, these open quantum systems have this has to do with various fields of recent quantum science and technology, like as I mentioned, quantum computation, quantum measurement, quantum thermodynamics and thermoelectricity, which I will mention, and quantum information, of course, simulation of quantum many body systems, quantum optics, quantum sensing, quantum transport, and nanoelectronics, etc. So what is open quantum system? So first, I should mention about closed system dynamics. That is, we know that when the system is isolated, very nicely isolated, then it can be described by the Schrodinger equation. That is the Hamilton. This is the Hamiltonian evolution, and we all know the solution here. This is a unitary time evolution. But to deal with open quantum systems, and especially to deal with mixed state, we need to use von Neumann formulation of quantum mechanics. So von Neumann, what he did, he used the density matrix from the wave function. He constructed the density matrix, and this is the von Neumann-Liouville equation. Actually, if you do the time derivative here, and if you substitute psi t from here, and do some little bit of calculation, actually here something is okay. Then the time evolution looks similar, like ut psi 0. Here, this is a state vector when you have a pure state, but here you can also deal with pure state using this von Neumann equation, but the advantage is here we can also deal with mixed state here. So sorry, as I said, we can deal with mixed state if we use the von Neumann formulation of quantum mechanics. So here I show how to obtain this Liouville von Neumann equation from these usual Schrodinger time evolution, the unitary dynamics. And as I mentioned that open quantum systems, for open quantum systems, we evolved the okay, let me first, yeah, this is the total Hamiltonian. To describe open system, we have a system Hamiltonian. This is the environment Hamiltonian, and this is the interaction between the system and the environment. So under this total Hamiltonian, we have the total time evolution, and then we trace out the environment to obtain the reduced density matrix of the system. So this rho S is the reduced density matrix of the system after we trace out the environment. This is the task, I mean, we do. And after doing that, we are only interested on the system part, because we have traced out the environment. And usually this time evolution looks like what I have written here in long time limit. They are not described by a single unitary evolution, so they can be described using multi operators, they sometimes called Krauss operators. But this is only for in long time limit. But here what we will do, we will also have the advantage to deal with this time evolution. I mean, we will describe how the system density matrix and their properties will evolve with time. So for that, we will start from the microscopic Hamiltonian of the system environment and their interaction, and then we will see how to obtain the density matrix of the system after tracing out the environment. Okay, this is a particular approach which is called perturbative method. So perturbative methods are useful or can be used when under some so this is an approximation. I mean, this is valid only under weak coupling, when the system interacts with the environment very weakly. And there are other Markov approximations also are there, so I'll talk about that. So here we can see we start with this Born equation. This is the total Hamiltonian, that is the system, environment, and the interaction. We go to interaction picture, standard interaction picture, we go, and then in this picture the Born equation becomes this, and we integrate this equation to obtain this, and we integrate here, and then we substitute this again here. This is like a recursive method. And then after that we use several approximations, which are, as I mentioned, that not valid in general, but they are valid under certain experimental circumstance, which nicely describes the results of the experiment. But beyond, if we go beyond that limit, then some interesting physics will emerge, and that will also, I mean, it is hard to solve, because as I mentioned, this is a many body problem. So most of the time we are not able to solve this exactly. So we need to take the approximations and go ahead, I mean, and proceed. So with this approximate method, after doing all these things, finally what we get is a quantum is a master equation. We used to call this as quantum master equation, and this is called the Born Markov master equation, where this is this right hand side, there are two parts. One is the Hamiltonian part, which looks similar to a unitary time evolution, but this is another extra part coming out, which describes the dissipation process. Okay. Okay, this comes from, actually, when we substitute when we substitute this here, actually we obtain this equation, last equation. So I have written that here, and I should take one example. These are very abstract, so let me take some example. For example, a damped harmonic oscillator, where you have this oscillator Hamiltonian and then the environment and this the interaction between them. And we go to the interaction picture here. We need to apply some operator time evolution techniques, and then we finally obtain this, and then we define this one. Let me see. With this interaction Hamiltonian, we define this is noise operator, and if we substitute this into that equation, we obtain the master equation actually after tracing out the environment. So and as I mentioned that we actually apply several approximations. One of the most important one is the Markov approximations, where uh, you have these bath correlation functions, because they will appear here. They will appear in the master equation, because if you break the commutation relations, then and trace over environment is there, so we will have this kind of bath correlation functions. And to calculate that, we need this spectral density of the environment, because this k are the kth mode of the environment. As I mentioned that if you see the Hamiltonian, these are the the environment is actually modeled. This environment Hamiltonian here, this environment is modeled with infinite number of bosonic or mode, or the environmental excitation mode. So they have a energy distribution, or we call them if we know the energy distribution, that is a spectral distribution of energy, whatever. So that actually comes here. That is also related with the density of states. So these bath correlation functions are very, very important. And we finally obtain the Born Markov master equation. Actually, here later I will show that we will go beyond. Here actually, let me see. That is given here. Okay, here the t going to infinity here. Actually, this is the Markov approximations. Under this approximation, actually, we obtain this Born Markov master equation. But as I said that under some physical realistic situations, this kind of approximations are not valid. So we need to go beyond Markov approximation. This is an example of two-level atom interacting with their environment, where we describe the decay processes, decay of two-level systems. And this is a quantum dot system interacting with these electronic reservoirs. Yeah, as I mentioned that this for non-Markovian systems, where the where the Markov approximations are not valid. So there are many systems. For example, in case of in the initial slides, I have shown some examples where non-Markovian effects are present in those systems, ranging from solid state physics to hybrid optomechanical systems, quantum chemistry, even in quantum biology, quantum transport, and electronic nanostructure and quantum optics, where the back action, sometimes we call back action, because the system also have some influence on the environment, that is the back action, are typically significant for finite size structured environments at low temperature. So under those situations, those approximations are not valid. So we need to go beyond Born Markov limit, and we need to handle with these non-Markovian open quantum systems. So and there are investigations where it was it was shown that non-Markovian systems can be used as a resource in quantum technologies, where these are very useful, uh, especially for ultra fast quantum devices. So there are some non-Markovian, how to measure non-Markovianity. We did some work, so we just skip this. We have studied the entanglement dynamics, that is disentanglement dynamics under non-Markovian. I mean, non-Markovian means it is not anonymously accepted. I mean, which is Markovian, which is non-Markovian. So people are trying to quantify non-Markovianity using various, in different approaches actually. So here I better I say beyond, we go beyond Born Markov approximations and see where your decay rates are not constants, they are time dependent, and we see how we see the departure from their Born Markov counterpart. So these oscillations are for non-Markovian case, and these blue lines are for Markov cases as well. So some studies also we have done some studies for non-locality, quantum non-locality dynamics. That is how do they behave under non-Markovian environment. And we also use Legette-Garg inequality to probe non-classicality in an open quantum systems. That is, the system is evolving under a dissipative environment. So this Legette-Garg inequality is a type of Bell's inequality, but the correlation functions are here. This Q is some observables which is measured at different times, and we construct using these correlation functions. We construct some inequality, looks similar to Bell's inequality, but here we have single in Bell inequality we have entangled states. So we have different at least two different systems we need, and we measure locally, I mean, to the subsystems and try to see how they are correlated. Here actually the correlation is between here we consider a single system, but the correlations are between the observables which are measured at different times. So one can say that this is a kind of Bell inequality in time domain, but anyway, this has nothing to do with entanglement. Okay, and for open quantum systems, actually, not much work is done. Now, gradually, people are studying in the context of open quantum systems also. Okay, these are some the physical systems with which we work. These are some open quantum systems, and these are the results which I skip here. Yeah, two different type of Legette-Garg inequalities. Here we also consider a dephasing environment, and we also study the non-classic we try to probe the non-classicality under this dephasing environment, how the systems still behaves quantum mechanically, not quantum mechanically. I mean, we have some non-classicality, and that is this violation. When this inequality is violated, we say that this is non-classical. Okay, non-equilibrium transient dynamics of photon statistics. This is again here. These correlation functions are actually two-time correlation functions. So these two-time correlation functions are important for various reasons. Apart from the density matrix, actually, these two-time correlation functions are important quantities. For example, in photon statistics, we have G2. That is, here we have investigated uh, the G2 dynamics, actually, for this kind of non-Markovian environment. In the steady state, also we have explored a new type of phase transition of photon statistics. Okay, we have also investigated the time dynamics of quantum coherence, and how this coherence is distributed. Coherence is distributed. Oh, sorry. Let me go among various qubits. Okay, let me explain here the system here. So here we have three two-level systems, which both individually, I mean, this two-level system interacts with a thermal reservoir here. This one is interacting with another thermal reservoir. This one is another thermal reservoir. So this is a multi qubit system. It is three qubit here, and they interact with their own local environment, and we see the dynamics of the coherence between different parts. I mean, because we have three different qubit, so the coherence is distributed among three of them, and there are total coherence, global coherence, and global coherence is also distributed in two different fashion, bipartite and tripartite fashion. So we see the dynamics under this environment also. Okay, yeah, these are the mathematical model I try to skip here. uh, Fragility of quantum correlations and coherence in multipartite photonic systems. We have recently published this experimental. We have collaborated with the experimental group. So this is an experimental paper. The theoretical part we have actually explored. These are the tomography of the qubit density matrix, three qubit system. Exact decoherence dynamics of 1/4 of noise, because uh, most of the nanoelectronic devices, they encounter this kind of noise, actually 1/f noise. So this is very important for different systems. So we have actually explored the exact dynamics of I mean, we treat in the previous literature, actually they treat the 1/f noise classically. So here, with the full starting from a full Hamiltonian, we actually we investigate the exact decoherence dynamics of 1/f noise for a superconducting resonator interacting with a general environment, non-Markovian environment. And these are the pictures are for the Wigner distributions for different initial states, how like from the left to the right they decohere. So that's why this picture faints. Okay, this is another very important approach to deal with open quantum systems, which is actually developed by Professor Wei Ming Zhan and his group in Taiwan, in Tainan NCKU. Actually, I have worked with him. He was my postdoc supervisor. So we have published some papers, and I quickly mention about this approach here. So this path integral approach under we using coherent state representation. So this is a non-perturbative exact master equation approach, which is applicable to a large class of open quantum systems, applicable for both weak and strong system reservoir coupling. And from this master equation, actually, we can reproduce these perturbative master equations under exact limit. So both bosonic and fermionic systems can be handled with this approach. So this path integral approach, the basic discussion I skip here. Okay, so what we do the exact things exactly what I have shown in the initial part. I mean the Born Markov master equation derivation. So here also we have a density I mean total density matrix. Total density matrix here is this row. Okay, so this rho st is the reduced density matrix of the system. And how do we obtain that? We obtain that as I mentioned, that we evolve evolve the initial state. Initial state, what was the initial state? Initially, the system was in some initial state rho is 0. Environment was in some initial state. Usually, we take it as a thermal equilibrium state because the environment we treat as a heat bath or reservoir. So, reservoir consists of an infinite number of excitations, and they are in thermal equilibrium. Usually, the standard approach is that the reservoir is in thermal equilibrium. So, rho e actually is some thermal equilibrium state. Rho s is an arbitrary initial state of the system, and they evolve under this unitary evolution. This unitary evolution is constructed by the total time Hamiltonian. That is, total Hamiltonian is system Hamiltonian plus environment Hamiltonian plus the system environment interaction Hamiltonian. And then after they evolve, we take the trace over the environment to obtain the reduced density matrix of the system. And here is this basis, because any density any operator in quantum mechanics, we can expand it in some basis, right? So here actually we consider coherent state basis here. So using that, so this tracing over the environment is a tricky part. So after doing that, actually we obtain the time evolved density matrix of the system only. That is the reduced density matrix of the system, which looks like this. So if here is this is rho s0, and this J is the propagator. The propagator is obtained after we trace out the environment. So and once we have the propagator, we know how to calculate the time evolution of the system using this equation. And this propagator for this kind of open system, this is a standard Hamiltonian, which is called Fano-Anderson Hamiltonian, which was this, I mean, Fano resonance and Anderson localization was described using this kind of Hamiltonian. And so this is the system part. This is the environmental part. Environment can have one of a reservoir, that is one thermal bath, or two thermal bath, or many reservoirs. So that's why this alpha actually means here. This is the interaction part. The propagator, using that tracing over the environment, etc., all after doing all these things, the propagator looks like this, and they are actually this J1, J2, J3 are functions of these quantities U and V. So they all of these, I mean, they are determined by two very basic functions, this U and this V. So they are the most important functions here. They are called Green's functions. So these functions U and V are analogous to the non-equilibrium Green's functions of Swinger-Keldy's theory. So U is recognized as the retarded Green's function. They are also here. That's why I was telling that two-time correlation functions are very important things in open quantum systems, apart from the density matrix. And V is another Green's function, is called lesser Green's functions. And this U and V satisfy this kind of integral differential equations. Most of the time we cannot solve them by hand, but we can solve them with computer and under an arbitrary spectral density of the environment, or the density of states of the environment. Okay, so here we can see that the equation for U, that looks like a Dyson equation, so contains a quantity called small g t tau. This is two-time correlation functions kind of thing. And V, once we have obtained U, we can also obtain V, which also contain another function g tilde. So how does it look? I mean, I should show you here. This g and g tilde looks like this. So if we know the spectral density of the environment, then we using the Fourier transform, we can have this. Okay, g tilde contains n bar. N bar is the particle distribution of the environment. I mean, like for bosonic reservoir, this is the Bose-Einstein distribution, and for fermionic reservoir, that is for electronic reservoir, this is a Fermi-Dirac distribution. So this describes the thermal fluctuation, because these distributions contain the temperature here, and this g actually there is no temperature here. So this function u actually describes the dissipative part, and this v actually describes the fluctuation part of the environment. Okay, and there are these solutions which were again obtained by the group of Professor Weimin Zhang, and they analytically solved that. And in case we cannot solve, if we are not able to solve analytically, sometimes we use numerical techniques. Okay, and once we have the propagator, we determine the propagator here. After obtaining the functions, Green's functions u and non-equilibrium Green's functions u and v, we obtain the propagator. We can have we can actually derive a master equation, which is obtained using exact method here. So exact, I'm saying, because we do not take any approximation like Born or Markov approximation. So this master equation or this propagator time evolution is valid for arbitrary coupling strength. That means the system, whether the system interacts with the environment weakly or strongly, we can use this. So this is the master equation. This gamma is the dissipative coefficient. This gamma tilde is the fluctuation coefficient, and this HSR, this is the renormalized Hamiltonian, because we start with the Hamiltonian. The system Hamiltonian was, if we remember, here the system Hamiltonian was this H cross omega 0, but after the system interacts with the environment, we trace out the environment and we have this master equation. From this master equation, you can easily recognize that this is the Hamiltonian part and this is the dissipative and the fluctuation part. So this Hamiltonian is now renormalized with the renormalized frequency omega 0 RT, which is again determined by this non-equilibrium Green's function u, and this gamma tilde is determined by both u and v. Okay, so for different spectral density, these dissipative and fluctuation dynamics were, I mean, investigated, and for strong coupling, because strong coupling case was not much explored. So in the strong coupling limit, many interesting physics were actually explored using this technique. And okay, now I'm getting back to this non-equilibrium quantum thermodynamics for open quantum systems. So this is a relatively new field of research, which is again related to the open quantum system dynamics. And yeah, this from our recent paper, I have taken this. Okay, so the system interacts. Okay, this is open system. The system Hamiltonian, reservoir Hamiltonian, the interaction Hamiltonian, and the reservoir is initially in some finite temperature, and we trace out the reservoir. Or sometimes we say reservoir, sometimes we say it as environment. Okay, both are same. I mean, so what we investigate is that we investigate non-equilibrium quantum thermodynamics by generalizing the concept of various thermodynamic quantities like temperature, heat, work, free energy, that depends on the details of quantum states and their dynamics. So the emergence, how the equilibrium thermodynamics emerge out of quantum dynamics. This is the thing, and we say that the all thermodynamic laws are preserved with our formalism of non-equilibrium quantum thermodynamics, which we have. And another interesting case we will describe here, where we have dynamically we see a negative temperature or dynamical phase transition, and the third law, how the third law emerges. So here is a non-equilibrium quantum thermodynamics formalism we have given in that paper. So basically we see how dynamically, I mean, so we see the real-time dynamics of quantum thermodynamics. So no, it is not like in some thermal equilibrium state, one thermal equilibrium state to another thermal equilibrium state. So in the middle, what is happening when the system is evolving? So we can trace out the real-time dynamics of the thermodynamic quantities. So temperature is defined, so it is like in equilibrium thermodynamics, we have the temperature is del E by del S. So once we have the density matrix, we can calculate the average energy, right? So this is the average energy, that is, and the entropy, we have used Born entropy here for the system. Okay, and the free energy is defined similarly, but here we can see here all these thermodynamic quantities are time dependent, and first law of thermodynamics is obeyed here. So the heat is time dependent heat transfer is this, and also second law is also obeyed, and free energy always decreases. So here first I show you some figures for weak system reservoir coupling when the system, okay, and how this thermalization, that is how the system gets thermalized, and that can be described dynamically. I mean, so here we start with this total Hamiltonian, and we take out the trace over the environment, and we have the density matrix for the system. And the weak coupling limit, we can easily show that in long time limit, actually the system, if we trace out the environment, and we only focus on the system density matrix, and then finally it will emerge to the, so this is the thermal equilibrium state for the environment on the right hand side. And in the long time limit, actually the t going to infinity is somehow deleted. In the long time limit, we have the system have this kind of form. So this is a give state. This is the system Hamiltonian, and the system is, we used to say that the system is thermalized. Now, okay, and okay, and this question, actually, how thermodynamics emerges from the microscopic quantum dynamics, is an important issue raised by many others. To address that, we consider a simple system like a photonic system in contact with a hot bath. So we consider first the initial state of the photonic system in some energy eigenstate. So this En0 is in some energy state initially, and after doing all these the open system techniques, we obtain the reduced density matrix for the system rho t. Here I have not written s here, but yeah, it is implicit. So this final state of the reduced system becomes this one. So this W describes the various probabilities of obtaining various probabilities, the probability of finding the system in some particular eigenstate n. So Wn n0t are the probabilities. So they are time dependent, because yeah, we want to observe the time evolution of all the thermodynamic quantities. So again, they are determined by two fundamental Green's functions u and v, which we numerically solve. And U actually in the long time limit, because it is a dissipative process, and that function actually decays. So U goes to 0 in long time limit, and V, that function V actually, this is only for the weak coupling case actually, when the system very weakly interacts with this environment. So this V goes to the Bose-Einstein distribution, and the density matrix rho actually in T going to infinity, W goes to this form, and where n bar is the Bose-Einstein distribution. So the reduced density matrix finally, so this is exact, we can write this density matrix in this form then. So this is the canonical Gibbs form, and we say that this system is thermalized. So thermal equilibrium has been reached. So this is the case under weak coupling, and how this thermalization occurs here we can see very clearly. Okay, but of course we can see the time evolution also. I mean the real time dynamics. So for that we have, as I mentioned, that the this is the initial state, this is the final state, this is the final state is written in this form, and this is the entropy, average energy, temperature. All of them are time dependent. Yeah, free energy. Okay, here the energy, these are for different coupling strength. These different colors actually for different coupling between the system and the environment. All of them are in the weak coupling regime actually. The eta c is some critical value actually. Beyond that, we say that it is uh, strong coupling. So energy actually increases when the system interacts. We plot here the energy, entropy, temperature, and the free energy with time. So we see the dynamics here. Okay. Okay, sorry. Okay, I have only a few minutes. Okay, so this is the time dynamics of these quantities, and here I show how they reach to equilibrium. That is, in long time limit, the energy and the entropy goes to the maximum, temperature goes to the reservoir temperature, free energy goes to its minimum. So this way actually we can trace out the dynamics of all thermodynamic quantities. This is also those thermodynamic quantities are plotted here for different initial state of the system. So this again the emergence of classical thermodynamics from quantum dynamics of the system in the weak system reservoir coupling regime. Yeah, this is another interesting scenario where when the system energy, initial average energy of the system is comparable with the reservoir energy. Reservoir energy, I mean KT0. KT0 is the thermal energy of the reservoir, right? So if the average energy of the system was initially in comparison with the reservoir or less than the reservoir energy, then this phenomena actually occurs. Energy actually then is absorbed by the environment from the system. So the system energy actually here decreases, and the entropy increases initially because the system when the system interacts with the environment, as I said, that it gets mixed. From the pure state it will be go to the mixed state. That's why the entropy increases here initially. But if the temperature is very low, like here zero temperature case is the blue line, so then the system will eventually go to the ground state. So that's why the energy actually go to the zero level, and they have entropy also actually increases, then the entropy decreases. So the third law of thermodynamics, that is the entropy should go to zero at zero temperature, so that is actually recovered. And in this scenario actually you can see del E by del S it becomes negative because energy decreasing and entropy increasing. So in this scenario we have a negative temperature case, and And this negative temperature case was investigated or realized with various physical systems recently. And this is a dynamical phase transition we have investigated in the same paper, when the system energy is less or comparable with the reservoir energy. So this color picture on the left side is for the energy, and this is time and temperature. So this x-axis is time, y-axis is temperature. Here also x-axis is time, y-axis is temperature, and the color contour is, the left one is energy and the right one is for the temperature, the time dependent, the time dependent temperature. So we can see that these for this temperature, when the temperature of the environment is in the is comparable with the system energy was also taken 5. So here we have this quantum classical border, we can say, or dynamical criticality or dynamical phase transitions here. Okay, now we go to the strong system reservoir coupling case. This is also similar, exactly the similar case. So when the system interacts strongly to the environment, okay, this was the original Hamiltonian of the, this is system environment and the environment system interaction. This is the master equation. This is the renormalized Hamiltonian. So only thing is that for the strong coupling case, we need to renormalize the Hamiltonian, because due to the system and because of the strong interaction, the system Hamiltonian is renormalized. So that's why when we calculate the average energy, we need to take this renormalized Hamiltonian. So only that is the difference for the strong coupling case. I mean, we have to be careful about that. But for weak coupling, we also can consider this. But for weak coupling, actually both are the same. But for strong coupling case, we need to take this extra caution. And rest of them are all the same, like temperature and all these other thermodynamic quantities are defined similarly. So this is a total real-time formulation of that is non-equilibrium formulation of quantum thermodynamics, where we can study this real-time dynamics, and this we believe that we will have wide applications for different systems. And for example, I mentioned in my initial slides, and all thermodynamic laws are preserved with our formalism of non-equilibrium quantum thermodynamics. And these are some future planned quantum heat engine we will explode, and non-equilibrium electron transport through quantum nano devices, and some thermodynamic properties, because this approach, which I mentioned, developed by Professor Zhang and his group, is applicable for electronic systems also. The only difference is that now these coherent states are described by Grassmann variable. They are not just complex numbers. They are complex, Grassmann variables, because the electronic system, we have to be careful of when we exchange two Grassmann variables, their sign will change. So this is already developed for electronic system as well. So current and conductance, all these things can be calculated for this kind of system. Okay, thank you very much.
Okay, thank you, Moni. I guess there will be questions. So people can ask questions.
So can I ask one question?
Yes.
So you mentioned that at some stage you mentioned that you don't make approximations. But I am assuming that is only if I start with a certain simplified model, and after that, beyond that, you don't make approximations. So yeah, what I wanted to ask you was basically what's the connection between your approach and this Lindblad method? It looks like they're pretty much the same, or are they different?
Okay, so may I know who is speaking?
Okay, I'm Girish Setlur. I'm a faculty here.
Okay. This is a nice question. Thank you. This Lindblad master equation, which you talked, yeah, because in quantum optics, we basically use this kind of master equations very often, right? And they are very successful master equations. But again, this Lindblad master equation, what you mentioned, are derived under certain approximations. And here, what we are actually trying to explore the regime where, I mean, we want to go beyond this regime where this non-Markov, Born Markov master equation will not be so. Maybe it will not predict exactly the physical scenario or the real situations. If we are stuck with a very short time regime, the transient regime, and then the correlation functions, the Bath correlation functions cannot be approximated to the delta type, the time correlation in delta. So and
Yeah,
also
I can fully relate to that. Yeah,
recoupling is for example, if you have a strongly coupled system, then also you cannot use that master equation. So then we need to go beyond that.
Yeah, so my last follow-up to that is that given that, because I have myself worked on this in the context of non-Markovian Coulomb screening long time ago during my PhD. So there, one of the, Tony Leggett told me that if you don't make controlled approximations, no one will believe you. So I had to struggle a lot to find a controlled approximation which works in the ultra-transient regime. So, my question to you is that do you have anything analogous to a controlled approximation that you make in the situation where you have these very short transients?
Transients. Okay. I have not actually how to say categorized in this way. Actually, we actually only see weak coupling and Markov, and then we go. But you are right that we need to gradually lift the approximations and try to see whether whether it is a good enough approximations under that circumstance.
Yeah, I mean, you have to explain what is a small parameter because there's so many things happening all at once. So, and the other question is that is this is it conserving approximation? Kadanoff and Baim has mentioned in their book that such approximations you have to make sure that they're conserving. For example, I think in the Lindblad method, the trace is 1. The trace of rho is 1.
Yeah. I mean, whatever you do, the certain things have to be satisfied. That is, the density matrix should remain a density matrix. I mean, it should be a positive operator and an Hermitian. Yeah.
Okay. So that's also the case when you have very short transients.
Yeah, and in the strong coupling case, because here actually you solve exactly. I mean, you have the propagator and everything. And then actually the problem comes when you do some approximations wrongly and try to predict something which is beyond that approximation. Then comes the problem. I mean, then the density matrix will not behave actually like a density matrix.
Yeah, okay, thanks.
Yeah, okay, thank you.
Other questions? Any other question from the students?
In the chat box, there are some questions.
Chat box. Okay.
No, no, sir. I don't see any question.
Surojit Doloi asked some question.
Surojit had asked one question. Can you please elaborate how you differentiate between local and global coherence in your context?
Okay. Let me go to the slide. Okay. Actually, when you consider a multi-qubit system, like here we consider 3-qubit system, right? So the coherence is at different level. So you have coherence at single qubit level. Also, the coherence is at 2-qubit level and 3-qubit level. And first of all, you need to define what actually coherence is. I mean, how to quantify coherence. So that is quantified. I mean, like here, using entropy, using von Neumann entropy actually. So you this rho d, if you can see here the screen, this rho d is a diagonal density matrix, and this rho is your original density matrix. So the distance between, so this is a kind of distance using entropy. I don't know, relative entropy. This is called relative entropy. So relative entropy between your system, the density, actual density matrix, and a diagonal. Diagonal means there is no coherence. All the off diagonal elements are zero. So then, how this? How what is the distance between? I mean, how to say? How far they are? I mean, what is the difference between them? I mean, if you consider a completely non-coherent state, uncoherent state, like a diagonal state, and then you see the entropy difference between them, then that will, in a sense, quantify how much coherence you have in your density matrix. Similarly, for tripartite state also, here this similarly actually this coherence is defined. Okay, so if you see that this paper, the scientific report paper here also, all these quantities, so I should suggest you to look into to go through these two papers. That is, one is the scientific report 2019 2363. Another one is the experimental paper which I have mentioned. This one, physical review A paper of 2020. Here actually you will have very clearly yeah, it is mentioned how these different coherence quantities are calculated using entropy. Is that okay?
Okay, there is Best Planto. He is putting the question, can you please explain the quantum versus classical regions in that KT0 versus
okay
versus H bar omega plot?
Okay, the last one, this dynamical phase transition. So here if we divide this contour plot in the middle, if we write a straight line here, so we see that, okay, here also the energy, okay, the blue line, the blue contour is the regime when your reservoir temperature is much less than the initial average energy of the system, right? And so in this case, actually, energy, how does that evolve with sorry, how does that energy evolve with time? Energy actually decreases, you can see. And if you go beyond that temperature, this is KT0. So let me see. Yeah. So in this regime actually the energy, this is energy plot. So energy actually increases. So this is one thing. Another thing is that here the temperature, the dynamical temperature is we plot it here. So that if I see this is contour plot is for dynamical temperature, right? And so here also KT0 is 5 here in the middle. So when the reservoir energy is comparable or less than the initial system energy, then we have this phase transition. That is, this blue curve is, you can see from the contour plot, this is negative temperature here. So this blue represents the negative temperature, and the upper one there, the red, the positive temperature. Okay, so from negative temperature to positive temperature, so we only see negative temperature below this line. Above this line we have the normal thermalization. So that's why we called it the upper one is the classical regime, and when we see this the lower part, that is the when the reservoir temperature was very low compared to the system energy, I mean, or comparable with the system energy, that we call it very low temperature reservoir. So there is that's why we call the quantum regime. Yeah.
So Debu has put one question. Can you please explain a bit more on the Leggett inequality, which is the measure quantum property of the system? How are they different from Bell inequality? Mani.
Bell inequality. Okay. Thanks. Nice question. Debu, I think I met you in Taiwan, right?
Yes.
Okay. I recognize you. Okay, so the Leggett inequality. So if you see the original paper by Leggett and Tony Leggett and Anupam Garg, in that paper actually the title was "If we don't see the moon, whether the moon is there or not." So something like that, catchy title. But in that paper actually they constructed this inequality. So it looks like a Bell inequality, but these correlation functions like CJI, they are actually Q is some observable we measure on the system, and TJ and TI are two different time. So okay, this like Bell inequality. In Bell inequality, we assume the two assumptions. That is, Bell inequality says that when it violates, we say that there is no local realistic theory in quantum mechanics, right? Quantum mechanics doesn't support Bell inequality. Likewise, here also, quantum mechanics actually doesn't support sorry. Can you hear me?
Yes, carry on.
Okay. Yeah. So likewise, Bell Leggett-Garg inequality was constructed. Bell inequality was constructed using the locality and reality assumption. Leggett-Garg inequality was constructed using two assumptions. One is called macro realism. So two assumption was that one is that the system has its values, means whether we measure or not, it has those values. Another one assumption was that the measurement doesn't disturb the system. So if we apply those two assumptions, then actually one can show that quantum systems actually violate these inequalities. So that's why we say that when it violates, it means some kind of non-classicality is there in the system. So yeah, two assumption. One is that system has those values even if we do the measurement. Then before measurement it has values, and another one is that the measurement doesn't disturb the system. Under this assumption, they constructed the inequality, and it was shown that the quantum systems actually violate this inequality. That means some kind of non-classicality is there. So we probed in the context of open system how it violates. I mean whether this non-Markov environment helps or not. Yeah.
So one more question he had asked was, is this independent of the Bell inequality, or are they related?
Okay, so it looks like the Bell inequality, right? Because Bell inequality is also constructed from different correlation functions. But the thing is that Bell inequality, you need at least two subsystems. One part is at with Alice, or another part is with Bob, right? They can be separated. I mean, they can be far apart. And then in one part you do some spin measurement or two-level measurement, and another part also you do the two-level measurement, and you see the joint measurement probabilities, and you see how they are correlated. And for some entangled state, when you have entangled state actually violate that Bell inequality, right? So local realistic theory, I mean quantum theory doesn't allow local realistic theory.
Is there any more question?
But here we have only single system in the Leggett case.
Okay, if no more questions, I think it's time to thank Moni for this wonderful presentation.
Okay. Okay, thank you, Santosh.